Hello everyone, welcome back to the latest lecture session. I believe we were well into looking at different aspects of air pollution. In that context, we were trying to understand, let's say, why different plumes given out at the ground level or slightly above the ground level would, let's say, reach different levels of the atmosphere at different seasons. And why is that important? Because let's say we are concerned with the effect at the receptor, which is, let's say, the humans at the ground level, or we are also concerned about transport of the contaminants over longer distances, let's say, right? So in this context, there are two aspects to understand, obviously. One is the temperature of the air, out there, right? It obviously depends upon the ambient conditions, let's say, the environment on that particular day, right? Environment typically meaning radiation, heating up the earth, and then the air near the earth's surface heating up, let's say, right? We are concerned with the ambient temperature profile. The second aspect is, as you know, I guess, as you move away from the earth's surface, pressure, I guess, decreases, and you are going to have obvious effects with respect to decrease in temperature. So let's say if I release a packet of air or a plume at the ground level, as it moves up, it's going to cool down. So here we have air and, let's say, ambient air and also the plume at different temperatures. So as we know, cooler, relatively denser, it's going to be at the bottom, hotter, relatively less dense, and it's going to try to rise to the top. So this is essential because you want to have lateral mixing of the pollutants so that the pollutants are not concentrated at the ground surface, right? So that was the background that we looked at, and in that context we were about to, or rather we started discussing some general aspects, right? And what were they? I guess we know that wind direction and speed, obviously this is with respect to advection, transport of contaminants, right? And this is with respect to cloud cover and its relevant effect on radiation reaching the earth, and thus the different temperature profiles, let's say, right? Radiation reaching the earth is going to heat up the earth's surface, and you are going to have different temperature profiles near the earth's surface accordingly at different seasons. And thus temperature profile, obviously, I guess, because relatively different densities, you are going to have churning, right, or mixing in the relevant air or atmosphere right above the earth's surface, and that will lead to turbulence. So you will have mixing out there, and obviously precipitation, let's say, right? But I guess we are going to be looking at these aspects because they concern us, yes. So we were looking at different stages or different kinds of what do we say, transport out there, and it depends upon how the conditions are. We are concerned about two aspects. One is, let's say, how will my packet of air, if it's released from the ground, how is it going to change temperature? That's something that we have out here. And the other one is, how is the temperature of the surrounding environment, let's say, or the surrounding air or the ambient lapse rate, let's say, right? Why is that? Because we are now comparing, or it's relative, right? We are concerned with relative densities out here, and that's what we are going to see. So here I guess we have what do we say, the dry adiabatic lapse rate. It's what does it tell us? It tells us that for each 100-meter increase in what do we say, height or distance from the ground surface, the temperature is going to decrease by 1 degree centigrade. And the case that we have here now, or the one that we are looking at, is about or is giving us some idea about neutral stability, let's say, neutral conditions. And here the slope or the ambient lapse rate is same as the dry adiabatic lapse rate, right? That's what we see. That's why both the two slopes are aligned out here. So how do we understand this? Let's say there is a pocket of air out here, let's say, right? And let's say I push it up by 100 meters. Let's say I push it up by 100 meters, right? So what's that profile going to be? It's going to be here, right? But as you see, the temperatures of both the packets of air, I mean, I pushed it up by 100 meters. I guess the scale is slightly bit off, maybe 300 meters it's here. So okay, it is right, I guess. So because the temperature change is actually 1 degree centigrade per 100 meters, I guess, right? So that's something to keep in mind. Anyway, so if I push it up by 100 meters and now the temperature, ambient temperature decreases by 1, the what do we say, the packet of air that we are concerned about or that we are pushing up, let's say, is also decreasing by 1 degree centigrade, right? So it's what is it now? So it's at the same temperature as the surroundings, so relatively same density, thus there will be no further movement. Let's say if I push it down, let's say, right, let's say I move it up out here with respect to 100 meters, let's say, push it down, let's say. So then I guess we are going to have the temperature out here decrease or increase by 1 degree centigrade, right, from 21 point, let's say 3 or 4 to 22.3, let's say, right. And obviously what do we see again? The temperature increased both with respect to this packet of air and also the ambient air, you know, beside it, let's say, right. So obviously again relatively same density, the volume at rest or the packet is at rest because it's the same temperature as the surrounding. So let's move on. So let's see what happens when I guess different stable states, right, different states of stability, unstable state. Let's see what it is that we have out here. Again, height on the y-axis or along the y-axis and temperature along the x-axis. And dry adiabatic rate, you know, that's what is this out here? I guess that should still be 1 degree centigrade out there, but maybe the ambient lapse rate seems to be relatively different out here, right. So it's minus 1.25 degrees centigrade per 100 meter. So what do we see? A packet of air that's out here. Let's say if it is pushed up, it's at B, let's say, right. So that's going to decrease by what now? Where is this? Let's say 1 degree centigrade, right. 21.15 decreases to 20.15. But obviously, as we see, this lapse rate, ambient lapse rate is relatively higher. So it decreases relatively more, right, the ambient profile or the environment temperature at that particular height, 400 meters, is relatively, what now, is it lesser? So it's lesser, right. So if it's lesser at this place or point, pardon me, at 400 meters, so what's going to happen to this parcel? It's relatively what do we say, higher temperature compared to the surrounding area, right. So thus it's going to keep rising, right. So that's what you see, it continues to rise. So same case, if I push the packet down, let's say, right, let's say somewhere out here, let's say, or let's say because of conditions of the graph, let's say out here, let's say, what do we see out here? Again 21.5, it's going to increase to 22.5, right. But here the ambient temperature, I guess, is now relatively more than this particular packet of air, again because the slope or rate of change of the ambient what do we say, conditions or temperature is relatively higher than the dry adiabatic lapse rate. So obviously what's going to happen, this is what do we say, this is cooler and ambient temperature is this, volume continues to sink. So what do we have out here? We have the packet of air to be relatively, I guess, let me look at it out here. The packet of air is out here and that's this temperature, the ambient temperature is out here, right. So this packet of air is relatively cooler than the ambient temperature, that's what we see out here, right. Packet of air is relatively cooler than the ambient one. So obviously if it's cooler, relatively denser, so it's going to keep sinking, right. So as you see, it's unstable out here, right. That's why we see, because there is churning along the or in the vertical direction, let's say, right. So that's the unstable condition outside. So if it's stable, I guess it's obviously the inverse, right. So here you have the ambient lapse rate to be lesser than the slope, I guess, to be lesser than this 1 degree centigrade per 100 meters, which is the case for the dry adiabatic lapse rate. And it's now 0.5 degree centigrade, decrease in temperature per 100 meter increase in elevation, let's say. So what do we see out here? Let's say from here we are pushing, let's say, the packet up, and let's say at 400, let's say, what do we see? What is relatively at lesser temperature, I guess? The packet of air is at relatively lesser temperature, right, and the ambient atmosphere is at higher temperature. Is that what we also see in this graph? This packet of air is relatively cooler and the ambient temperature is relatively hotter. So that's why this is more denser, and obviously it's going to come back to this, even though it's pushed up, it's going to come back to this location where it was emitted from, right. Let's say if I push this packet of air downwards, let's say, right, and let's look at this graph out here. So what's hotter and what's cooler? So the surrounding temperature, the ambient one, that is out here. So, the ambient one, that's out here, and the dry packet of air which was pushed down, that's out here. And as you see, your particular ambient temperature or the environment is relatively more cooler. So, this is going to come down, or rather this is going to, let us say, move up, let us say, right. So, it is going to move up here, right. So, that is what you see out here. So, it is stable, even though we displace it, right, we emit it with some velocity, it is going to end up at that particular point. So, that is what we see. So, that is why it is stable, right. So, three classes, what did we talk about? We talked about neutral stability, right, or neutral conditions, that is relatively better term, I guess. Neutral conditions, we talked about neutral conditions, if you push it, it is going to be, or it is going to be, what do we say, it is going to follow the profile of the relevant atmosphere. Unstable, right, even some displacement, it is going to lead to mixing and thus dilution of your polluted. But when it is stable, obviously, as you see, it is going to be concentrated at a particular, what do we say, distance from the Earth's surface. So, this is obviously an issue of concern. So, let us see what we have. The other one is inversion, when it is very stable, let us say, right. So, here as you see, I guess this should have been positive, is it? Okay. So, here as you see, the ambient temperature actually increases, right. The ambient temperature actually increases with increase in height, let us say, right, or as you move away from the Earth's surface, the temperature is actually increasing. So, this is called inversion condition, and it is remarkably stable. Again, it is you can just follow that. So, I guess not guess, it is more or less an extension of the stable conditions which we discussed out here, right. It is remarkably stable out here, as you can see, right. So, this is something you want to avoid here at all costs, right. Why is that? Let us say, okay, I believe I have the graphs next, or some of the figures which will help you understand that. So, inversion, I guess, when we see inversion, let us say typically it is early morning or late night and such, the Earth's surface is pretty cool. So, all the air near the Earth's surface cools faster than the air that is farther away from the relevant Earth's surface. So, temperature profile maybe could look something like this, let us say, okay. Because Earth's surface is so cold during the winter months, especially during the night, the air near the Earth's surface cools faster than the air farther away from the what do we say, Earth's surface. So, here it is what do we say, the Earth's surface, and here is with respect to elevation, and this is temperature here on the x axis, let us say, right. So, what do you see? If any hot air is sent out, you can look at the relevant what do we say, lapse rate and such, I guess, right. And once it is going to reach here, right, this is, let us say I am emitting my packet of air, or I am burning something here at the ground level, and this is the dry adiabatic lapse rate minus 1 degree centigrade per 100 meters, let us say. So, as you see, it is going to go or use this profile, and then once it is at this temperature, it is not going to, it is at the same what do we say, density as the surrounding air. So, it has no motive to either go up or down, and that is why it is stuck out here at this level. And obviously, the issue here is that all the pollutants are now packed, there is no dispersion in the vertical direction, and thus you see the concentration of the pollutants at the ground level is remarkably high. Let us see some other examples. So, I guess inversion at another power plant out here, right. You see this, even though they are emitting it with considerable velocity, it is again maybe coming down out here. And I think this example is similar to what we saw with respect to the plume rise and what do we say, stable layer in the civil engineering department or near the civil engineering department, right. So, that was the similar, or that is the similar profile that we have out here. So, one aspect to consider is, with respect to, let us say, coastal regions or land breeze during night, let us say. So, when it is warm, okay, or let us say during the night, let us see what is going to happen. So, warm air over water rises and air over land cools and descends, and thus land breeze, I guess, is in this direction. That is what we are trying to say. In the morning, I guess the land breeze seems to be from the land towards the what is it now, water, let us see. But during the day, I guess what is going to happen, again due to differential levels of heating of the land and the what is this water surface, what do we see? We see that warmer air, relatively warmer air over the land. So, warmer air rises and cool air, what do we say here, right, it cools. So, the land breeze or the breeze is going to be from the over the water into the land, I guess, right, or towards the land, pardon me. So, what is that going to create an issue? So, this is what it can have, let us say, and keep in mind that this was during the day. And I guess what do you see? You see that with some inversion layer, let us say, the pollutant, let us say, that was near the coast or such, it can be carried far, what do we say, inland, right, and because of the inversion layer, it is not going to go up and it is going to be concentrated way out here, right, way out here meaning near the earth's surface. Again, different temperature profiles, but we can look at this in detail later, I guess, right. So, that is something to keep in mind. So, stability, let us just have a quick recap. So, dry adiabatic lapse rate, temperature decreases due to lowering of pressure, and what is that value? It is 1 degree centigrade per 100 meters. But again, keep in mind that we have been so far referring to it as dry adiabatic lapse rate. If it is moist, it is relatively different. It is where is this now? Minus 4 degrees or 6 degrees, okay, 6 degrees centigrade per kilometer though, I guess, or 0.6 degrees centigrade per 100 meters, right. So, relatively lower again, but most of the industrial emissions from industries, they typically follow the dry adiabatic lapse rate again. So, obviously, if temperature falls faster, absolutely unstable, this is something that we have already looked at. Temperature falls lower, absolutely stable. If it is between, it is neutral conditions, I guess, right, or conditionally unstable. Let us move on. So, if height is this, temperature is this, so minus delta T by delta Z, what is that equal to 0.1? This is with respect to the packet of air. So, that is 1 degree centigrade per 100 meters, and we know that dry adiabatic lapse rate, okay, this is with respect to the ambient conditions, pardon me, and we know that the dry adiabatic lapse rate is also this, right. So, obviously, we are, or it is going to be relatively more stable, let us say, right, relatively more relatively stable, let us say, or rather the term I guess was neutral, pardon me there, the term we are using is neutral, let us say, right. And the other aspect I guess is when it is lower than 1, right. So, obviously, it is stable, and we already looked at the graphs, you can go through them if you want to. And the other one is obviously when the ambient what do we say, temperature decreases at a faster rate than the dry adiabatic lapse rate, which was 1 degree centigrade per 100 meters. So, it is unstable, and you want to typically have these conditions because it promotes lateral mixing. So, whatever I give out at the ground surface, it is going to be dispersed laterally, let us say, right. So, that is pretty worthwhile. Again, general graph, but again we do not need to mug up such stuff obviously. But one aspect is inversion, because I believe we looked at the data with respect to air quality index, right, and I think we looked at Anand Vihar and such, and we saw that in November of what, 2014 or 15, I guess 2014, the values were what, 1500, 1200, 1800, and when the threshold was itself was 500, I guess, right. It was pretty poor, and it is going to get pretty poor too every day, not every day, pardon me, every year along during the winter time, I guess. So, why is that? It is due to temperature inversion, right. So, again, two types of inversion. Typically, the one that we see is due to radiation. When thermal radiation at night from the earth's surface, I guess I should have explained it better out here. Thermal radiation at night from the earth's surface into the clear sky, I guess, right. Again, so in the winter, obviously not enough radiation, let us say, the earth cools faster, right, and it also cools the air nearer it faster. So, that is why you are going to observe inversion or temperature inversion. The other one is subsidence inversion, when which is the case when we have a layer of air descending with a high pressure, okay, let me reread that, descent of a layer of air within a high pressure air mass, right, descending air increases in pressure and temperature. But again, this is at relatively higher altitudes, but that is something relevant to, right, but typically we are concerned with radiation out here. So, the issue is that here you can have what is this inversion conditions, let us say 10 am. Let us understand what we have out here. So, let us say this is the profile. Yes, at 2 a.m. you have inversion conditions. At, I guess I should have had it with at 12 noon and such, that would have been better. But again, let me see at 3 p.m. let us say, when the sun is at its peak, nearer the earth's surface, it is going to be relatively hotter, and as you move away from the earth's surface, the temperature is going to be less. That is why the profile is like this, let us see. But in the night, the air nearer this particular earth's surface is going to be cooler, right? And only or this is going to cool at a faster rate than the air above, and that is why you see inversion out here, right? This is inversion out here, right? That is something to just keep in mind, yes. And at 10 a.m. though, the issue is that you can have, what do we say, you will have, what do we say, the earth's surface heating up, pardon me, and then you are going to have this layer of air heating up, and that is why decrease in temperature as you move away from the earth's surface, but then this layer again still follows inversion, but obviously slowly but surely it will move on to this profile, right. So, that is something to keep in mind. Let us move on, again inversion, right. One aspect to note is that we are typically concerned with where this inversion layer is, or where this, what do we say, layer between the cold air and warm air is, right. Why is that? Because that determines the mixing depth. Because if the mixing depth is too low, obviously the concentration of the pollutants within this limited depth and thus volume of air is going to be very high. But at least if this inversion layer is relatively higher, then obviously you are going to have some level of dispersion, not dispersion, I guess, yes, dispersion is the term. So, here you can see inversion typically in the hilly areas or valleys, this is typically more pronounced, let us say, right. So, that is something to keep in mind. So, subsidence inversion, again associated with atmospheric high pressure systems. Inversion layer is formed aloft due to subsiding air, and it persists for days. But again, in this class we are not really going to look at that in great detail, I guess, right. Again, inversion layer, subsiding air within high pressure systems, I guess, right. So, subsiding air, again we will not go into this in greater detail. So, subsidence inversion, this is what we have out here, right, and this is night and early morning, and in the daytime this is the relevant inversion. So, combined with both, this is what we can have, radiation inversion and subsidence inversion at the top, let us say, right. This is also quite often seen, let us say, right. So, let us move on. So, I guess just to understand with respect to the mixing depth, in the night it is going to be the lowest, obviously, because it is inversion layer. In the morning relatively higher, right. This is the profile in the night, inversion temperature, and this, let us forget about subsidence inversion for now, let us say. And in the night, obviously, let us say if anything that I give out here, and the dry adiabatic, let us say my starting temperature is, let us say 20 degrees or such, I know the dry adiabatic lapse rate and such, let us say. So, I can calculate the mixing depth, let us say, right. For example, in the night what happens, this is, please note that this profile we have the ambient lapse rate or the environmental temperature conditions, let us say. And okay, this temperature is given along this axis and height here, obviously. So, let us say what do people do during winter nights when they feel cold? They burn, what do we say, they burn your leaves, wood, sticks and such, let us say. So, let us say if my temperature of packet of air is somewhere out here, I know the dry adiabatic lapse rate is something, let us say the slope is like this, assume that. So, my mixing height is going to be somewhere out here, and that is what you see, I guess. In the night it can be pretty less. So, whatever we burn for heat or such in the night, especially in the winter, where does it stay? It stays near our breathing environment. That is obviously the reason why we do not want to burst crackers, especially in the night, especially in the winter season, let us say, right. So, that is what you see. But in the early morning, obviously at 9 a.m., 10 a.m., when the earth just starts to heat up, you see a slightly different profile. So, the mixing, what do we say, depth increases, and obviously later on in the midday or such or afternoon, when the temperature profile is like this with respect to the atmospheric conditions, we have the mixing depth to be pretty high. So, that is why typically in summer season or such, you see pretty good what do we say, air quality. Why is it? Because the pollutants are now relatively more dispersed, or relatively more, or the concentration is relatively less, right. So, that is something to keep in mind. So, one aspect here is, I guess you can read about this Lake Noise disaster, I think 1980s or 85, I think, let me just say 1980s. So, carbon dioxide, I guess, was emitted from beneath this volcano. There was buildup, and I guess equilibrium issues or such, and wave conditions maybe, and there was a spillover. Keep in mind that it was 80s. I can't remember the month, but certainly I am sure that it occurred in the night. And again, night inversion conditions, let's say. So, something that was given out, let's say, wasn't really going up, right? And also you can calculate the molecular weight of carbon dioxide and air, or let's say 78% nitrogen and the other, let's say 20% or so of oxygen, let's say, right? And you can look at the molecular weight and which one is heavier, right? So, again, carbon dioxide, I guess, was considerable carbon dioxide was given out, right? And thus being heavier, again, inversion conditions, probably, as I mentioned, it occurred in the night. So, all this was transported along the ground surface to the local nearby villages, and you have had many people dying. And I guess I just wanted to look at or present a relevant picture out here. Cattle and people dying. Why? It's colorless, odorless. So, people really don't know or can't, what do we say, figure out what's happening out there. So, again, this is from, I believe, the Lake Noise disaster, right? NEOS disaster, right? Carbon dioxide gas from the magma. Okay, I am unable to read this. Again, carbon dioxide was released in huge quantities and that traveled along, and then I guess looks like it was 50 meters thick layer of carbon dioxide, and you had considerable number of deaths of people and cattle out there. So, closer back home, I think we had the Bhopal Gas Tragedy, I think again 1980s, was it 84? And then what's this about? Again, keep in mind, I think this occurred in November, or was it December? To my knowledge, it was in November. Again, peak or winter conditions. And again, please note that it occurred in the night, either midnight or 2 a.m. or so, when the inversion layer was going to be pretty low, or pardon me, when the mixing depth is going to be pretty low. And even then, I think what was this, methyl isocyanide or some such gas which was released or leaked from the containers. What happened? Well, you know the rest, people have read it a lot. So, typically who lives near the industrialized zones? It's the relatively poorer section of the society, and obviously they bear the brunt and considerable number of deaths. And now you have soil pollution too. I guess recently we received a again, keep in mind that the year is now 2020 and 1984, I guess, so that's 36 years. So, again, we still have people suffering from the adverse effects, because once the pollutant is contaminate such a widespread area, you need remarkably high levels of what do we say, resources, monetary, right, and also human, to be able to clean it up, which is what I guess we don't have. Anyway, people are still suffering the effects, if not carcinogenic effects, certainly toxic effects, let's say, right. Again, one such relevant picture, let's say, right. And Chernobyl disaster, I think, was this also 80s? I guess yes, because I remember reading somewhere that it led to the demise of the Soviet Union, or rather it was a catalyst, if I may say so. Chernobyl reactor, you had, what is it, I think the third or the fourth reactor there blowing up, right, when they were conducting a test, right. The control rods, they had some such tip which actually triggered the explosion rather than stopping the relevant reaction, let's see, right. So, let's see what we have. So, here it's Chernobyl, and here at that time I guess USSR and such, USSR. So, as you see, because of the prevailing wind conditions, right, what do you see? All the what do we say, are considerable radiation, right, or the pollutants were taken all across Europe, right. So, that is something for you to keep in mind, the extent of what do we say, transport of air pollutants, let us say. Here we are obviously talking about increased radiation dose here, and obviously different graphs, and cesium deposition, I guess. So, I guess what did they see? Again, different zones were cordoned off and such, original 30-kilometer exclusion zone, but again you can understand the level of what do we say, transport here, or extent of transport, pardon me. And Kuwait oil fires, I believe, I think with respect to the Middle East, Saddam Hussein and the wars and such, I think they burnt them, right? Who burnt it? I can't remember it. So this is a particular figure. Oil fields were set alight, and people thought that these pollutants, I guess, are going to, be carried over multiple hundreds of kilometers, and I guess pollute a large, what do we say, extent of the population, not pollute, affect a large extent of the population. But I believe both deposition and precipitation led to or minimize the effects of this particular plume transport, let's say, or adverse effects of the plume, right? So, Icelandic volcano eruption, I guess, football lovers would have seen that this played havoc with it, right? Even tennis lovers, I guess, yes. And let's just look at it. So, this is the, what do we say, site of the explosion, and you see the extent of this particular fly ash or such that was sent or the plume that was sent all over the world, and that is why you understand the number of flights and such that were cancelled. Again, we are just looking at a few cases here which help illustrate the extent of transport of air pollutants, let us say. So, think of what do we say, let us say our thermal power plants or the Chinese eastern coast and such, and the level of transport that not the level, pardon me again, the extent of transport out here. So, looks like I overshot my time, and typically we are supposed to talk about that or follow on with respect to that story of our not, how can I put it, descent into anarchy, right, in after the collapse of the Mughal Empire. But I guess that's going to have to wait until the next session. And as usual, I will thank you for your patience.